can't change the address type here, or the video metadata type. So what kind of interesting data models can this lead to? How about storing JSON? So this is an actual real-world example. This is a product catalog. It's in JSON format. And so what I did here is I created a type called dimensions, which fits this part of the JSON field. I created a type called category, which fits many of the categories. And then here's my table creation. I have my dimensions, which is just a single type, but then also I have a map of categories now. So I can have one or many categories assigned to that particular product. And I can store JSON directly in Cassandra, but it's fully typed schema. And that really makes a difference when you're not really sure what you're putting in your database and you need schema. So, why? Cassandra for time series. That's, I would say, one of the primary use cases for Cassandra right now. This model's crazy, man. And because I have to keep true to my title, why is Spark such a great addition to Cassandra? And hopefully, by the end of this talk, not only will you believe me, maybe, but you'll maybe want to do it. So I'm going to give you an example. Because I'm an engineer, I like examples. I do not want fluff. I want to see something that happens. So classic time series data problem, weather station. You know, you have a time, a temperature, and a bunch of those. So a weather station collects data every hour, sends it to a Cassandra cluster. When I need to read it, I need it in this kind of format. So multiple hours with a graph that shows the temperatures. That's, you know, that's a pretty typical application for a time series database. This could be stock data or something like that. So how do I do this? So whenever you design a data model for Cassandra, you start with your data model and you start with your queries. So you have to ask your question. What kind of needed queries do I need for my data? So I want to get all data for one weather station. I want to get data for a single date and time. And I want to get data for a range of dates. You know, so I can do those pretty graphs. Well, so I have to support that. I have to store data per weather station. It has to be unique. And I have to store it to time series in order from first to last. And that first to last is pretty important because I want it in order so I don't have to figure it out in my application. So my data model is going to be interesting. It is one table that I'm going to put up here. So my data model has this table called temperature. And it's pretty simple. There's a weather station, and there are 4 components for the time. There's year, month, day, and hour. Now, I got this question last night. You don't have to break it down into components like that. You can use a timestamp as well. I'm doing this for more demonstrative purposes, so you can see exactly how it's laid out. As most good demonstrations are, it's much bigger than you probably would do in production. So that's what I'm doing here. And then there's one field here. It's a temperature. It's a double. So my primary key, what it's doing is I'm saying, my primary key means that everything in here means this is unique. So the combination of weather station, year, month, day, and hour is a unique data point. That solves one of my problems for my data model. The weather station in brackets here, I will explain why it's in brackets in a minute, but that makes it so that I get better data locality. So when I insert my data, this is CQL, Cassandra Query Language. Just it looks pretty similar, looks familiar. You're inserting data in here, so I'm inserting data every hour. So 7, 8, 9, 10, and there's different temperatures. This is a weather station in Norway, so it never gets warm. So we have now this data model where we can ask a question. Select weather station, hour, and temperature, where this weather station ID is really the coldest place I've ever seen. And it's actually not too bad. And with year, month, and day of December 1st, 2005. So when I ask for that data, I get it in this nice format, this row and column format. And that's useful for me from an application programmer because I get rows and columns and I can iterate over that. That's great. But why is Cassandra better at that? Or what makes it so good? Why do people choose Cassandra for time series data in this case? And it has to do with the way we store data on the disk. And this is a critical point. Your slowest component in your computer is your disk. We keep adding tons and tons of RAM. We make CPUs faster and faster. We make networks faster and faster. And we're still relying on a piece of spinning rust, right? And that is changing. We're now moving to SSDs, which is great. I have one on my laptop. It has changed my life. All right, I have a sad life, but it's very different type of I/O, and it's great. But we still have the problem where it's still going to be the slowest thing. Even an SSD is going to be your slowest part of your system. So what I want to do is I want to minimize how much interaction I have with the disk. If that's the slow thing, avoid it. So how does this work with Cassandra? So with the storage model, logical view, this is what the programmer sees. What's actually happening is this. We're actually storing the data in a sequential fashion in a file, a single file, on the disk. And when it writes this data to the disk, it's immutable. You no longer have to do random operations on disk. When I hear storage vendors tell me how they can give me as many IOPS as I want, I don't care. I want latency and transfer. That is what makes your database fast. IOPS are a good way to lie to your boss. So this is how it stores data. So why is this good? Well, this means that the way that it's laid out means I can get a nice order on disk. I don't have to reorder it if I ask for it. And then if I add more things, it simply tacks them on to the end. It appends them to the end. And this is done through a housekeeping operation called compaction. It'll combine files and clean them up and make them all sequential. This is awesome.
What happens if you don't get the data in sequence? If you get 8 o'clock the next day?
An excellent question. What happens if weather stations, and this is actually a very typical problem, you have a limited connectivity device. Maybe something that only talks once a day, but gives up all its data. So you have very high potential of out-of-order data. That out-of-order data is an expected problem, and this is what's built into Cassandra just by the way that it works. And that is, if you look at how we compare data and sort it on disk, it's based on a comparator. These right here, because they're part of my primary key, and thank you for asking this question, because that really makes the next slide good. This part right here, I will show you, is how we sort the data. So if something comes in out of order, it will get resorted properly. So here's my primary key. And how does this work? What is this? I want to show you how a primary key works. So when you go to use Cassandra tomorrow, or maybe even tonight, because you're that fired up, and that's okay, you know, I'm with you, man. I'm not going to say no, but get some sleep, okay? It happens. That's what happened to me. I had a friend of mine, his name is Adrian, he said, hey, you should try out Cassandra. I'm like, why? Because we're doing it in Netflix. I'm like, that night, it was a long night. Man, I left. Sounds like a night in Vegas. Anyway, so when I look at my primary key, this is what making all of what I just said work. So I start with my weather station ID. That's what we call a partition key. And a partition key is what gives you data locality. And I'm going to explain what that means to you in the long run. But that partition key is hashed using murmur3 or MD5. And that hash is unique because it's a consistent hashing algorithm. But then it positions that row of data, that storage row of data, on one server. And then it's replicas, how many you have. So if you have 1,000 nodes, only 3 of those nodes will have this weather station ID's data. That's important, because if you have that many nodes and you're out there doing a search for all that data, that's what we call batch. That's going to take a while. So the other part of this, we call clustering columns. Now, we call it that because this is how the data is clustered together on the disk. You used to see how they're batched together, or how they're grouped together on disk. The order is by the comparator. So if these are all integers, that means we're going to use the natural sorting order of integers for year, month, day, hour, given in combination. So when I take my partition key of this, now it will write the data on the disk. But then the clustering columns, look at what I have here. 2005, 12, 17, 18, 19. If you were to sort this using any sorting algorithm that looks at integers as a comparator, this is how it would sort out. So that out of order data that comes in later will fit in nicely here once it's reorganized.
It's an indexing structure.
It is an indexing structure, but more of a sequential maintaining system. You know, so I say this is my sort order, here's my comparator, the system takes care of it for me. And the out of order data is fully expected. So,
one question.
all right.
I'm sorry, how does this work with multiple weather stations? Because you potentially have hundreds of them, and you get events for many of them coming to.
I kind of want that. If I'm going to have a system that does 1 million writes per second, that's one event every microsecond.
But that's what I mean. I mean, do you kind of reserve a special place on the disk for one weather station, or?
Without getting too far into the write model, the simple, so I'll give you the simple tour of the write, how writes work in Cassandra. A single write, like a weather station with that one blip of data that has, here's my temperature and my year, month, day, and my weather station ID, that will get sent to a Cassandra server. It's written to a commit log immediately. Then it's put into a mem table. The mem table is a structure just like this in memory. Once it goes to the mem table and the commit log, it's acknowledged back to the client. It's just that quick. Now, if you notice, I didn't put anything on disk yet. Later, that mem table, which is this structure in memory, is then sequentially written to the disk. And then that file is immutable at that point. And it will continue to do this. This is log structured files. Yes?
But if you have multiple weather stations, you need to keep space between the weather station to, so to say, to insert future data in between, right? So
Well, let's consider this could be different files too. The weather station ID is going to be different for each one, and they could be on different nodes as well. You're not allocating space. It will, once a table or an SS table, which is our data file, is written to disk, it will never write to that file again. It will write another file.
So the sequential data is not written in one stream on the hard disk.
If it is in memory,
Yeah.
it is written in a stream on the hard disk. If data comes later, that stream will be written on disk. And then there's a process called compaction, which combines those files. It will bring them both into memory, do a recomparison, and write it back out.
And how do you do updates over the nodes? So
How do you do what?
updates over the nodes. So basically, when one client is updating one node and the second client is updating the second node.
Mhm.
So how do you?
How do you
Merge
get conflicting results?
Yeah.
Well, there's two answers. First of all, if you have a high chance of conflict, is that a problem? If it is, we can data model out of that. It's called the ledger model. If you know that it will happen and we can deal with it, last write wins. It's based on timestamps.
Okay.
So it's not based on anything more complicated than last write wins. Most times last write wins is fine, and if it isn't, I can data model you right out of that. There are plenty of ways to get away from that. So this is how a primary key works. This is how we sort the data on the disk. This is how we know where the server is. And that primary key, oh, man, I keep doing it. Ah. Chris, I hate your clicker. There. So the data locality is really a critical piece of this. I mentioned before, if you have 1,000 node cluster, and I put those into production all the time, you do not want to go looking for this, like where is that weather station? You do not want to ask every 1,000 nodes. So when it's hashed, it says, I know where it is, it's right here. And that's it. So when I get that one spot, then I can go back to this query pattern, which makes, how do I get this? This is the query that should run in just a few milliseconds or less. I've built these things that they've been less than a millisecond because you go to a single server, you ask for a very specific set of data, it comes right back at you. So here's a query pattern that's pretty typical. This is going to build out our graph. You know, it's going to have a range of data. So I say, here's my weather station, blah, 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 and then I put in this range. I want an hour from 7 to 10. Now, that's what we call a slice or range query. And what makes that unique now? So we've already sorted this data on disk. So now I get my partition key for locality. I know where the data is, so I find one server. And then I do a single seek on disk. Aha! That's also the key to speed. Because if you have a spinning piece of rest in your server, a seek can cost you 5 to 10 milliseconds. That's before you get data. Now, if I have to do multiple seeks on disk, I better hope that it's either in buffer cache or I'm going to be hitting the disk a lot. If I have to do 10 seeks and it's 5 milliseconds each, that's 50 milliseconds. It's just physics. So we want to eliminate how many seeks we do to 1. And that one seek on disk is important. Now, if I get a range of data, I just want to pull that off sequentially like that. Cassandra pulls it up into memory, presents it as rows and columns to the programmers, and programmers like this. From a programmer, developer standpoint, you don't have to really understand as much what's going on the disk, but I want you to know this is why it works so well. And this is why you can get those really fast millisecond queries if you build your data model correctly. In time series data, which there is a lot of, there's a company called Circa in Australia. They're a nonprofit. They collect every single trade data in the world. There's 2 million operations per second on the database. And they keep up just fine. And it's all time series data. And it's very fast and sequential. They have a mobile app that does this.
And how are indexes updated over the nodes if you're doing writing to different nodes? So
There's no indexes.
okay. So
Fixed it. No indexes.
but there is a cache. So how do you know that you need that the second node will basically get the same result as the first node? If you mentioned that you have the hash in the cache, and how is that?
You mean from the replicas?
Yeah.
So there's a concept called a consistency level that's set at the programmer. The programmer can set consistency level.
Yeah.
You can ask for a quorum of data. So if you have 3 copies of your data,
Yeah.
you ask for a quorum. That means 51% of those replicas give you the exact same result, the correct result. And that establishes that consistency. In a lot of cases, your data model may not need that kind of strict consistency.
Yeah.
And you can go down to a 1. But it's done at application level. You can use what's called, what we call lightweight transactions, where you can use Paxos and lock and have an exclusive operation on the, if you're doing, say, an exclusive update or insert, where you want to check the existence and make sure you don't have a race condition. We bring Paxos to that. Now, all of these, as you get more strict with your consistency, it's going to get slower. So it's a trade-off, and you can go all the way down to 1, or you can go all the way up to full Paxos transaction. Okay, so Apache Spark.